All right, welcome back to another video of 1MO3 structural property of materials. And in this video, I'm going to be talking about atomic packing factor and density. So far, maybe you have seen that atom could be made out of a model that are kind of like sphere. We have learned about simple cubic, we have learned about body center cubic, space center cubic, as well as hexagonal closed pack. So we have learned different type of crystal structure, and we also talk about that in general structure that are in general metal have this kind of crystal structure. What we will learn now is that let's find out how to calculate density, inferred density based on these kind of crystal structures. And by doing so, we can understand how different crystals have different packing factor, okay? So one of the things that actually originated from this kind of mechanics or this kind of calculation come from the 1600 period from Kepler. Kepler is an incredibly smart person, scientist in the astronomy field, but at the same time, he was actually doing a lot of mathematics, specifically in geometry, of trying to understand how those geometry are related back to astronomy. He had a very, very crazy idea of thinking about different type of polygon related to the orbital of the solar system. Turned out he was wrong, but he was inventing a lot of math at that time by doing this exercise. One of the cool mathematics that he did was trying to understand this very simple question, but apparently require a lot of math to do to prove that, was how many cannonball can you fit on a ship? And so you're asking, Bosco, why are you talking about cannonball when we're talking about atom? Turns out that mathematics that allowed Kepler to calculate how many cannonball fit on a boat can be used to calculate the density of metals and any type of crystalline material. Isn't that cool? So the reason why that is the case is that we can make a leap of an assumption that an atom is a spherical object, and by doing that, we can calculate the atomic spacing, and by doing that, we can calculate what is the density of a crystalline material. And I'll give you an example. Kepler was working on this problem, and he was trying to find out how many cannonballs can fit on a boat, and he found that there's actually many ways to stack these cannonballs. So here's his early publication, and he found that there's a Kepler conjecture. He worked out a solution, and he said that the closest pack you can have on cannonball is around 74%. And the reason is this sphere cannot fit space fully packed. There's going to be always some space. And if you can see here, this particular diagram, this square pattern on a 2D diagram, it has more gap than a triangulate or hexagonal closed pack structures. Turned out Kepler is so correct with this conjecture that nobody were able to derive the map until 2017. And the mathematician that derived and proved that Kepler conjecture is correct required 21 pages of math to prove this. So we're not going to return and go into those 21 pages of mathematical proof of Kepler conjecture, but we're going to show that the atomic packing factor indeed were also having similar behavior, where the highest packing density that you can have for crystal structure is around 74% by FCC structures. And indeed, this is this particular cannonball, kind of like a pyramid, have a closed pack structure, which is an FCC closed pack structure. So let's just begin with the journey of a 2D structure, which is what Kepler started with. And if you look at this particular structure, this may resemble, if you look at it from the edge of a simple cubic crystal. And this particular crystal, you can see that there's a huge gap there. There's a reason for that is because spheres, or in this case, circle, leave a lot of gaps. And so packing it like that is not the greatest idea. And it will leave a lot of room, and so it's not very efficient for shipping. There's other structure, and this looks like a little bit better, but turns out the closest you can pack in the 2D condition is this kind of hexagonal close pack where there's a prism. Sometimes we call this hexagonal close pack. The reason for that is because this resemble, when you put all this prism together, it resembles a hexagon. And you see this a lot in nature. If you pack a whole bunch of balls together, they're going to turn into that naturally. If you bring a whole bunch of straw together and you look at it from the top, the drinking straw, they look like this as well. And so it makes a lot of sense. And so we're going to use this kind of geometry to calculate the density of a crystalline structure. So one thing that I want to draw your attention to now is we talk about this 2D structure, which looks like a hexagonal close packed plane. And one thing that Kepler have found out, or actually the crystal structures material scientists have found out, is that a FCC structure has this kind of close packed plane. So let me just share the screen a little bit, and I'm going to show you right in front of me. I have a physical model of an FCC structure. Now, how do you know that it's FCC? If I look at the face, it's a face center atom here. Look at another face, it again have a face center atom. Every single face have a face center atom, so this is called a face center cubic structure. And this is, if you're asking about me crystal structure, this is my favorite one. The reason for that is when you split it in half, something really magical to see that appear. And I will show you right now. I'm going to just do something. I'm just going to take this physical model, a styrofoam ball. I'm just going to split it, okay? Nothing special other than just splitting it. And I'm going to split it in half and something look really cool coming out, okay? Look at that. This is the pattern that Kepler was talking about. This is the 2D close packed plane. Let me try one more time. This is FCC. This is close packed plane. This is FCC, right? Close packed plane. I love this. This is like an optical illusion. So what exactly did I do? I basically just look at the FCC crystal structure like this, and I look into the diagonal plane, and I split it in half. So this is a diagonal plane. Now, there, this is the close packed plane. So, turns out FCC crystal structure are just a whole bunch of hexagonal close packed 2D plane stacked together. So, let me go back to the slide, and you can see that this is in fact true for FCC crystal structure. So in the textbook, you'll see this kind of really largely stacked FCC model, and you can look into the diagonal of the lattice. So you haven't learned the terminology that, but you can think about that if you go in the x direction in one unit, y direction in one unit, z direction in one unit. So the 1, 1, 1 plane normal, you're looking at that 1, 1, 1 plane, you will see this kind of structure. So what is cool about FCC is not only is stacked in a closely packed 2D plane, it has this kind of what we call ABC packing. And the reason is that there's one layer that's shifted by one atom apart, and so that is layer B. And then it shifts again into the third layer, and so this is ABC stacking, and then the 1, 2, 3, and then the fourth line, it repeats itself, and it has the exact same geometry of the first line. So this is the second stacking sequence of FCC. So what I'm trying to say is that FCC have a very, very dense packing sequence. In comparison, simple cubic and BCC crystal structure are not close packed. And we'll show you how it works in the mathematics later. Another cool things about FCC is that it's actually very similar to HCP. So HCP, if you look at the crystal, you can see that the basal plane is already an hexagonal close packed structure. So what's different FCC from HCP is the stacking sequence, as well as the separation of the layer A and B. So FCC is always the closest pack possible. HCP, however, depends. HCP can theoretically be the closest pack possible, and at the closest pack possible way, the HCP is different from FCC only by the stacking sequence. So here we can see from the slide that the basal plane, layer A, and then after that we have an alternating layer, layer B, and then after that it repeats again to itself, which is layer A. So HCP have AB, AB, AB stacking sequence. So FCC have ABC, ABC stacking sequence, whereas HCP have AB, AB stacking sequence. Now, what is cool about HCP is that it could potentially be the densest possible, and here it is shown already geometrically, but it depends. The reason for that is HCP could be a little bit elongated. So, for example, graphite are these kind of elongated HCP, and so they're not very symmetric. And so, if you have the separation between the A and B layer are more separated, then what we call is that if you look at that crystal lattice, there's two axes. There's the lattice parameter A and the lattice parameter C. C is in the vertical direction. And so depending on the C to A ratio, you will find that HCP will have different packing density. Theoretically speaking, the highest possible density that HCP can pack is 74%, and that is also the packing density of FCC. So with all that said, let's try to calculate the atomic packing factor using the same branch of math that Kepler have worked on. So in order to do that, we need to make some assumption. So Kepler was working on bowling ball or cannonball calculation. So we need to make the assumption that the atoms are a perfect sphere with a radius of 1 or r. Okay. With this assumption, we can then start to calculate the atomic packing factor. This is a relatively good assumption for density calculation, but for other properties that probably is insufficient. Anyway, so here let us start calculating the packing factor of a simple qubit, and then after that use the same analogy, same type of mathematics to calculate the FCC, which is more complicated. So here in the diagram, you can see that we have a lattice, simple cubic lattice, with a lattice parameter A, and the lattice parameter is coincidentally equals to 2r, where r is the atomic radius of a perfectly sphere atom. So you can imagine this particular atom maybe having a nucleus in there and then have some kind of electron cloud, and the electron cloud is shared with another atom, and so that two atoms form this kind of spherical shape, okay? So how do you calculate atomic packing factor? So let me define what that is first. Atomic packing factor can be think of as the total volume of the atom put together inside that unit cell over the volume of the unit cell. And so if you look at the right-hand side diagram, in other words, I want to calculate the total volume of the blue part of that cube versus the total volume of the cube. And so what makes this material not fully dense is because of the white part, the part where the sphere does not cover, okay? So how do we calculate that? Well, let's define something first. Volume of the atom altogether will be equals to n times the volume of the sphere. And where n is going to be the number of atoms per unit cell. That does make sense, right? So I just want to calculate the total volume of the sphere or inside this this unit cell. All I need to know is how many spheres are there and how big they are. So in the case of simple qubit, n is equals to 1. And you probably have learned that in your high school, that the volume of a sphere is 4 pi over 3 times r to the cube. Okay? So that is just saying that this is 4 pi over 3 times r to the cube. Okay. Well, the volume of the cell can be calculated by doing this. Because it's a cubic structure, so the volume of the cell is just the lattice parameter time itself 3 times, so it's a to the 3 to the power of 3. In the case of simple cubic, a is equal to 2r, so I can rewrite this as that, which is basically saying the volume of the cell is equal to 8r cubed. The atomic packing factor will be equal to 4 pi over 3 r cubed divided by 8 times r cubed. So we can cancel the r cubed. Then what we'll get, you rearrange that, you'll get pi over 6, which is equals to 0.52. Okay? So what I'm trying to say is that this part contributed to about, or all the atoms together, contributed to 52% of the volume or space in the cube is actually the atom. The rest are just empty space. An empty space could be useful later on to actually stuck another atom, but for now, this makes the materials less dense. So let's find out another structure. Let's find out FCC. And just intuition tell me that just looking at this graph, FCC is denser. And so let's do the calculation, and just to confirm that our intuition is correct. And I will explain why this is important. Okay. So in FCC, the volume of the atoms put together is again n times volume of the sphere. Now, this one, remember from last lecture, we talked about that FCC have 8 corner atoms, so 8 times 1, 8, plus we have 1, 2, 3, 4, 5, 6, 6 base or face atoms, so half, and this gives us 4 atoms. So a unit cell of FCC have 4 atoms inside a unit cell, and so this is 4 for FCC. So see how the number of atoms in a unit cell become useful now? So maybe in the exam we can ask you how many number of atoms inside a unit cell for different type of unit cell. So for now, that means that the volume of atoms in the FCC crystal is just 4 times 4 over 3 pi r cubed, which is 16 pi over 3 times r cubed. Okay? And then the volume of the cell is the same as what we wrote previously, which is A to the 3rd. Now we need to be careful now because we want to convert A to R so that we can actually do this simplification and cancel the R out of the equation. So one thing that we need to know is just looking at this, and we need to say what is the A and R relationship. And so we have just drawn it here. So if we have 1 atom, 2 atom, 3 atom, so sorry for the poor drawing. So 3 atoms here. So this is R, this is R. So this is for R. And this is A, and this is A. So Pythagoras theorem said that A squared plus A squared equals to 4R squared. So this, if you do some simplification, that would mean that A is equals to 2 root 2R. And this is important because now I have an A and R ratio. Okay. So the A and R ratio is A is equals to 2 root 2R. And so I can substitute that back to the equation calculation, and I will have, this is 2 root 2 to the 3 times R to the 3. This is saying the same thing as 16 root 2 R to the 3rd. So then what is atomic packing factor? Atomic packing factor will be equal to 16 pi over 3 R cubed over 16 by 2 R cubed. And see, the reason I did the A and R relationship is so that I can get rid of this right now. And then I can get rid of that as well. This will give me pi over 3 root 2. So atomic packing factor, let me rewrite it so that's bigger. It's pi over 3 times root 2 over this multiplication, which is going to be around 0.74. So what have we just done here? It looks like just a whole bunch of math, but this is relatively powerful. This is saying something. This is saying that it is the simple cubic have actually almost 48% of the space is inefficiently used, whereas the FCC crystal have only 25 or 26% of the space being not utilized. Turns out Kepler calculation have stated that this is the highest packing density you can ever have in sphere, if the atom is sphere. So what it turns out is that both FCC and HCP tend to be more stable at lower temperature. And the reason it's lower temperature is because there's less entropy, and so the free energy of the system at low temperature would want to go to a packed state. This is called a ground state. There's some exception. Iron is one of those exceptions, but in general, material at low temperature tend to be in FCC form or HCP form. And then at higher temperature, they might change to BCC. Okay, but they are exception, and we won't talk about the details about the exception. Okay, so this is just the same calculation, so in typed form, so that you can look into it yourself. I suggest you to do this at home as following the math that I just did, but also at the same time do the calculation for BCC crystal, and so that you can get an idea of how to actually do this, perhaps in test, assignment, and exam. Okay, so FCC stands, and turns out this is the summary of what we have. Simple cubic are highly unlikely to be used because they're thermodynamically not very stable, because it's not fully packed, it's not very utilizing space, and there's often better choices, and the better choice are at least BCC or FCC and HCP. Now, I've shown you the density the atomic packing factor calculation of FCC, and you should do the same thing for BCC. But one thing that I want to mention is that because HCP has a similar stacking as to FCC, we can make that conjecture and make a extrapolation and say that HCP could potentially have also a 74% packing factor. But the requirement is that the C&A ratio has to be ideal. And the ideal C&A ratio is 1.63. C equals 1.63A. So with the atomic packing factor, you can tell which crystal in general are more stable, thermodynamically more stable. But another thing that you can use is to understand how to calculate the density of a given system, a unit cell system. So the density calculation is similar to what we have here. And this density is basically mass over volume, and the mass of a unit cell is N times A over Avogadro number. And N is the number of atoms inside unit cell. And so with that, and so that is mass. So this term is mass. And then density is mass over volume. And the volume of the cell is, if we're calculating a cube system, it's going to be volume of the cell is equals to A to the power of 3. It is worth mentioning that in this particular course, we are only going to be focusing on calculation of density of cubic system. We don't expect you to know how to calculate a hexagonal pack structure, because the math requirement is a little bit more complicated. But anyway, so here, for example, you need to think about the A and R relationship as well, right? So here, for the FCC, we have R here. So you need to know what is the radius of the atom, and after that, you can calculate what is the volume of the lattice parameter. You can calculate that lattice parameter, and then after that, you can calculate the volume of the cell. And by doing that, you can estimate what is the density of the materials, which is given in this form. Rho is equals to N times A over Avogadro number divided by V sub C. Another way of looking at it is that the first term, the left-hand side, N over V, is just number of atoms per volume. And then the right-hand side is mass per atom. And so if you put them together, you have mass over volume, which is density. Okay. So in the next video, I'll show you some practice problem of how to actually use this kind of concept to actually derive the density of the material. And this actually explains a lot of things. If you look at this, this would explain why one material are more dense than the other. And the reason behind it is related to two things. Either it's related to atomic weight. So this is the atomic weight. So maybe the atom itself is heavier. That makes sense. Or maybe the lattice parameter is smaller, and so the volume of that unit cell is smaller. So either the atom is heavier, or they are more closely packed, or have a smaller volume. That both can lead to a higher density. So it's related to the atom and also related to crystal structure. All right, thank you very much, and good luck studying.